Just started to recording. There is a message I see here. No, it is not a double. The HDH can be single or can be double effect or it can be more. Uh, it's not the issue of the number of effects. It's as simple as that we have one humidifier or two humidifiers or more. But the limitation is coming is that we have to have air. Air is the gas that carries the water vapor from one place to the other. And here we have some sort of a limitation in terms of the ability of air to carry moisture. The ability is limited by having the air being saturated. On the other hand, when we are talking about systems like this, the single effect evaporation compared with the humidification system, we do not have this kind of limitation here. We have other limitations, definitely, but not that one. That's why when we are talking about a single evaporation process, we are talking about a process in which we expect more and more production of water to be there. As you will see here, when we are talking about a system like that, we are going to assume, for example, that we are building a system that can produce 1 kilogram per second. A 1 kilogram per second is when you calculate that, for example, we are talking about 3.6 or 3,600 kilograms or liters per hour, which is about something like 3.6 cubic meters per hour. Multiplied by that 24 hours, you are talking about something in the order of maybe 90 cubic meters per day. So this is significant. It's not a matter of something that can produce. If you remember from the problem that we solved with HDH system, we were looking for a system that can produce 10 liters per hour. 10 liters per hour, this is in the design problem that can bring us to something like 240 liters per day. And this is it. Maybe you can make it bigger to produce 1 cubic meter per day as what you may have in your homework. And by the way, there is a new homework, which is homework number 2. It has been made available in Blackboard. It has 3 problems, and it is due a week from today, next Monday, inshallah. So back to the single effect evaporation, we are talking about a system in which we are not looking for a carrier gas. The vapor is going to move itself from one location to the other, which is basically, we have 2 major components in our system, so it's going to move from one component to the other. Looking at the objectives of the system, why do we need the system? Last time we said that, or we agreed that the system is not meant for industrial scale, industrial desalination scale, and this is basically for a simple reason. The reason is its performance is not the best. It has a poor performance compared to the other desalination systems that can produce massive quantities of water. It still produces much higher than the HDH, but we are talking about a different scale now. So when we are talking about the goal of this system, or normally we use an expression called PR, it is somewhere close to 1. But the quantities of water are huge. So what are objectives? Although we know that this system is not really found a lot in the industry, but understanding it is very important because this is the entry to understand the multi-effect desalination, which is one of the best systems that can produce water in a reliable and in a good performance way. So what we need to do here is to understand the system, to be able to analyze the system mathematically, develop a mathematical model that can show how the system is performing, to look at the performance parameters of the system that we have, and to have a look at what we call the evaporators. This is where the vapor is being formed, and maybe a little hint about the history of development of evaporators is going to help. This is, I just found this recently, some sort of a industrial scale uh, presentation of this system in which we have, it is basically made up of two components. One of them is an evaporator, which is this. The other one is a condenser, and the condenser is the unit where we can collect the sweet water and have it as a product. So this is more or less, we are basically talking about an evaporator, a condenser, and a tank to collect the water. And it may take several shapes. So this is one shape that I've just seen that looks like it's okay as an industrial shape. Um, this could be the one which is hidden. This could be a tank, for example, for sweet water, and there's another tank, one of them for sweet water, one for the brine. And then it has two components basically. So we're talking about two major components that are making up the system that we have. It has industrial limitation, yes, because it does not produce much. It does not have a high gore. It can be used on special applications like in marine vessels in ships where they do not want to carry water for the crew, the sailing crew for drinking, because this is going to be huge quantity of water, especially if they are traveling long distances and they need to carry material. I mean, you cannot imagine, for example, a tanker which is there to carry oil and transfer it from one country to the other, to have some tanks there just for water. They are better because they are moving in the sea. They are better take the seawater and desalinate the seawater and use it for drinking. That would make much more sense then. They don't have to store it. They have low performance ratio. That's right. Why they are important? As I mentioned a while ago, this is going to be the way or the entry for us to understand the multi-effect and then the multi-stage flash desalination systems. This is a schematic of the system. We are basically talking about two major components. One of them is what we call the evaporator. The other one is the condenser. So what would happen? And here in these systems, probably we need to keep in mind that we rely on steam as a source of energy. So the energy supplied to us in these systems are basically supplied in the form of steam. And this is why these systems are going always to be located near power plants. So this combination of a Rankine cycle and a gas turbine, you are talking about a combined power plant, and a desalination system is typical, especially here in Saudi Arabia. So you will find that in Aziziyah, we have desalination system, and El Jubail, we have desalination systems. In Yanbu, we have desalination systems, and so on. So that is basically some sort of a combination that you will always see when we are talking about thermal desalination. Al-Aziziyah, Al-Jubail, Yanbu, and other definitely. Now, the point here is these systems, you said that we have power plant. In the power plant, you have the Rankine cycle, for example, in which we have a pump, a boiler, a turbine, and a condenser. And normally we extract one line of steam from the steam turbine. And this line of steam from the turbine is going to be our source of energy here. So you take steam at low pressure, low temperature relatively, and you are going to have the steam enter here. The steam is going to condense inside the tubes. When it condenses inside the tubes, it leaves off its latent heat of condensation, HFG of steam. This HFG multiplied by the mass flow rate of the steam is the quantity of energy, is the rate of energy input to these systems. This energy is going to heat a thin film of water sprayed on the outer surface of the tubes. So this is seawater, which is going to be sprayed on the outer surface of the tubes. Tubes inside have steam, outside it's the seawater. It's going, number one, to sensibly heat the seawater from this temperature to the saturation temperature, and then part of the seawater is going to evaporate. The vapor will rise up here. It will pass by a mist eliminator, because if you have lots of vapor going up and there are droplets of water going down, the vapor can carry some droplets. We don't need these droplets with us because this is droplets of salty water. So we put like a filter here, a mist eliminator here, to prevent any entrainment of the liquid droplets with the vapor. So the liquid droplets will fall down. The part that will not evaporate is going to fall down, and we call it brine, which is a concentrated solution of salty water. This is going to be rejected back to the sea. Whereas the vapor that passed by the mist eliminator is going to be taken here in a pipe or a tube, where it will enter into a condenser. Inside the condenser, there are tubes. The tubes are carrying cold seawater to help in the condensation process. Normally, we need to condense all the vapor. That's why we use lots of seawater here. And we don't need all of that seawater for the evaporator, but we take more seawater that we want. So there is cooling water for the cooling process, and there is a quantity of the feed water that should enter here into the evaporator. So this water will fill the shell of the shell and tube heat exchanger, and it will cool down the vapor in the condenser. It will condense it so that the condensate, which is passing, the condensate is in the shell side. The vapor comes to the shell side, and we are going to collect it as sweet water here, desalinated water. Whereas the cold water that has entered, it will be preheated. We take the preheated water, part of it will be thrown away to the sea, and the rest is going to enter here to be sprayed in the evaporator. So we're talking about a condenser here, which is sometimes referred to as a feed preheater. So it's a condenser, and meanwhile, it is a feed. Because it is here to recover some of the energy and preheat the seawater before it is fed into the evaporator. So this is basically the system that we have to operate here. Any questions so far?
Clear.
Okay, since I see no questions, then we can proceed. And having a further look, you'll find here this system has some drawbacks or disadvantages. The disadvantages that we have here are basically you are taking much more water that you need here in the condenser. So you have to have some relatively big pump, and this water you are giving energy into it from the vapor. So after heating the water from tea cooling water to tea feed, you are throwing away part of it. So you are basically throwing energy, dumping energy to the surrounding. This is one problem. The second is you have used steam here to heat the seawater. Part of the seawater will evaporate, but a bigger part is going to be rejected. So you are rejecting seawater here, which is at a higher concentration, but it is at a saturation temperature. So you are losing energy here as well. You are throwing away energy to the surroundings. And as a matter of fact, this is why this system has low performance ratio or low GOR, gain output ratio, because of that, because you are throwing two streams of energy to the surroundings. One of them is the seawater that has been increase to the feed temperature. The second one is the rejected brine, which is at considerably high temperatures, almost saturation temperature at its given pressure. So that's why this system is not finding itself as a substantial, dependable system that you can find in the industry. It's because of that issue. So it is made up of two units, an evaporator and a condenser. The evaporator basically is having some tubes, as you can see here, this red tubes, and it's given in red here because I just want to indicate that this is the source of heat and these tubes have steam passing in. Sometimes this tubes or set of tubes is called tube bundle. And you may have more than one tube bundle in the unit, depending on how much water that you need to evaporate. So the tube bundles, and basically when we are talking about a design of the evaporator, what we are interested in the word design is how much is the surface area needed here, so that you can determine what should be the length of the tube and how many bundles that you will need. Definitely length, diameter, and how many bundles, which is basically, it's some sort of a pi dl as you have studied in your heat transfer course in the heat exchanger. So we have heat exchanger tubes, tube bundle. We have sprayers like showers here to spray water in the system, which are these. And then we have mist eliminator, demister, sometimes it's called demister, which has the same meaning as the mist eliminator. So we have the mist eliminator, we have the tube bundles, and we have the sprayer system. There is a pool here. It's a volume which is down there to collect the brine before you reject it. And we have a condenser, which is nothing more than a shell and tube heat exchanger. So that makes the whole system components. The condenser or the preheater, usually it's a shell and tube heat exchanger operating counterflow arrangement where the latent heat of condensation of the vapor is the source of heat that is used to preheat the seawater and definitely condense the vapor there. Whenever we are dealing with systems like these, parameters we might be interested in include how much cooling water do you need from the sea to make sure all the vapor will condense in the condenser. What is going to be the T cooling water? So if you are talking about a desalination system of this type, which is located close to the sea, so the point here becomes how much the performance is going to change from winter to summer. Definitely, in summer, the temperature is about 28 to 30 degrees centigrade in the Gulf. In winter, it can go down to 13 to 15 degrees centigrade. So the performance of the unit is going to be dependent on how the weather temperature is affecting the seawater temperature. This is going to affect the system performance. Unless you have something to do there, I mean, to remedy for this. One of the parameters we are interested in is how much is the heat transfer area in the condenser as well as in the evaporator. What's the overall heat transfer coefficient and how the overall heat transfer coefficient can be affected by the performance. Seawater is coming, seawater is salty. It has ions like calcium sulfate, calcium carbonate, magnesium hydroxide. All of these are kind of salts that at high temperature, they start to precipitate or they start to stick to the surfaces, making a layer of scaling, which is acting like an insulating layer. So scaling, fouling is another issue. It's just a heat exchanger, and the problems of heat exchangers are basically fouling and scaling. So fouling is there. If you remember the overall heat transfer coefficient expression that you used before, right, in the heat transfer course, used to have something that has been called fouling factor or fouling resistance. So the water which is coming is not very pure. Even if you use some filters, there is some sort of fouling that can be in the form of impurities coming with the water, or biological fouling by bacteria or so. So that's something that can stick to the surface and make a layer of insulation, reduce the heat transfer rate, and definitely reduce the evaporation rate and the productivity rate. So these are parameters that are affecting the performance of the system through affecting the overall heat transfer coefficient. How much feed is coming, how much water that we need to take from the sea. This water needs to be chemically treated by anti-scaling agent, anti-foulants, anti-foaming, so that you can just eliminate or at least reduce the effect of this kind of problems in the system. The salt effect becomes more significant as the temperature increases. It comes at a certain temperature and the salts start to precipitate. It is isolated from the seawater and it stays on the surface as crystals, as salts. And that's something that you need to avoid as much as possible. That's why you put some chemicals in the seawater before coming to the unit. And this is what we call pre-treatment. We did not talk about pre-treatment in the solar still or in the HDH system, because most of the materials there are made of plastics. So you don't worry about rust, you don't worry about scaling, but here we do worry, because basically we are talking about units where we need to transfer heat as efficiently as possible, and that's why we use metallic surfaces. The boiling point elevation, again, or the boiling point in the evaporator depends on the kind of chemicals that you add to it to prevent scaling or to reduce scaling and fouling in the unit. This is how the temperature changes from one unit to the other. Cooling water enters in the condenser. Look at the very right side of this figure here. So this is the cooling water. This is the inlet seawater to the unit. So seawater enters into the condenser, which is, as we mentioned, it's a counterflow, or more basically, it's a shell and tube heat exchanger, where vapor is there. Vapor is going to condense at a constant temperature. This is a change of phase. So this latent heat of condensation given by the vapor is going to be used for preheating the seawater from T cooling water to TF. And the letter F here, we mean feed. So this is we call feed water temperature. So we have almost a linear profile here, where in the heat exchanger, in the condenser, the seawater heats from T cooling water to T feed. And then it enters to the evaporator. So this part here is for the condenser, whereas this part is for the evaporator. In the evaporator, what will happen? You have steam that's going to increase the temperature from T feed to T boiling, which is the saturation temperature of the seawater there at the given pressure. If the pressure is 1 atmospheric, then it would be heated to 100 degrees centigrade, but that normally does not happen. We normally operate the evaporator at lower pressure so that the saturation temperature becomes less and you can get more vapor, as we agreed upon. Steam is coming from the power plant, it condenses here, and then after it condenses, we return back again to the power plant to get into the boiler and complete the cycle, the Rankine cycle there. So it's a line of steam extracted from the power plant, which is going to be the heat source to heat the salty water or the seawater from T feed, inlet feed temperature, to the evaporator, to the saturation temperature, which is TB, T brine, and then evaporation will take place, and evaporation takes place at a constant temperature. Then, after that, vapor is going to form. The dotted lines that we have here are indication of a couple of things. Number one, here, the vapor is at a temperature less than the temperature of the vapor that leaves the evaporator, because there are pressure losses in the pipelines due to friction and due to minor losses, and that reduces the temperature a little bit. So temperature of the distillate vapor in the condenser should basically be less than the temperature of vapor in the evaporator. However, you'll find that in analysis, we take them almost the same, like we neglect the pressure differences, but you would know that this is an approximation. The second thing is that the vapor temperature that forms in the evaporator is less than the saturation temperature by something that we call boiling point elevation. What is that? Water, pure water, boils at 100 degrees centigrade if it is under atmospheric pressure. But if you bring seawater at atmospheric pressure, it will not boil at 100 degrees centigrade because it's not pure water. It has salt in, and that makes it probably boil at 101 or 102 degrees centigrade. This difference is due to the existence of salt in the water, and the difference between the saturation temperature of the brine or boiling temperature of the seawater and boiling temperature of pure water, this difference is what we call as the boiling point elevation. The boiling point elevation increases as the salinity increases, for example. So it becomes a function of salinity and function of pressure, definitely, and at what temperature level that we are talking about. So this is the temperature profile, what happens in the condenser as well as in the evaporator of a single effect desalination system. At that stage, anybody had any questions?
Yes, doctor.
Doctor?
Pardon me for my question, but the condenser is used to decrease the temperature. If you condense something, you decrease the temperature, right?
Actually, we condense it. What we assume is that the vapor which forms in the evaporator is going to enter the condenser as saturated vapor, and it will leave as saturated liquid. So you don't have an intention to decrease its temperature, but you are taking the latent heat of condensation, which has to be released out to convert it from vapor into liquid. And this is the latent heat that you use for preheating the seawater.
So the entering state of for the condenser is cold water, right?
Yes, on the cold side, it is the cold water extracted from the sea, and this is preheated to the feed temperature at the exit of the condenser.
All right, I see. Thank you.
Any further questions?
Doctor, how can the pressure drop affect the temperature?
Because it's vapor. Remember, in your thermodynamic courses, sometimes if you are talking about highly superheated vapor, you may consider it as an ideal gas. So the relation is PV is equal to MRT, so pressure and temperature are related. Even in pure substance, if you do remember the figure that you have, which is the pressure temperature relation, if you are talking about saturated pressure versus saturated temperature, you'll find that there is a line like that. The higher the pressure, the higher the saturation temperature.
You're
And
right.
we have even talked about that in terms of desalination in general. For thermal desalination, we try to operate it at lower pressure because at lower pressure, the saturation temperature is low.
You're right, right. But isn't it in fluid mechanics, if the pressure change, then only velocity and head loss are affected?
As long as you are talking about a single, a compressible, for example, compressible fluid, we are talking about a single phase, only liquid or only air. When you increase its velocity, the pressure is going to reduce. This is according to Bernoulli's equation. But when you are talking about the saturated condition, at what pressure, saturation, temperature will be affected, that's another story. I'm not talking about a compressed liquid here, but I'm talking about basically some sort of a saturated condition where the saturation, temperature, and pressure are interrelated.
Oh, I see.
Okay. Any further questions? Fine. Mist eliminators basically are, they call it netted wire mist eliminators. They are basically something like filters, and the filters have a function of preventing the seawater from being carried or entrained by the vapor, so that the vapor has always to be pure. We do not want any droplets of water to get into the condenser. It will corrode. Seawater is an aggressive kind of compound because of the salts that it has. And you must have seen that. I mean, corrosion is there whenever units are close to the sea. Even houses through the sea, you can find that they need to paint it every probably couple of years or so, because the seawater is aggressive in nature. So we do not want the seawater droplets to be carried to the condenser, and we have to get rid of it. And that's why you put a mist eliminator. So the condenser should not have any brine at all. And we talked about the drop of temperature, which is because we are talking about vapor. So vapor, pressure, and temperature are interrelated. And normally, any drop in pressure is accompanied by a drop of temperature. The condenser, there's another issue here, which is one of the problems that we face in operating the evaporator and the condenser. You bring in seawater, and seawater enters to the evaporator, and they start evaporating. By evaporating the seawater has some compounds, which are the salts, as we said. It has calcium sulfates, it has calcium carbonates, and the carbonates is a problem because when you start heating it, they start to liberate gases like carbon dioxide. Carbon dioxide does not condense. So we have a problem of what we call non-condensable gases that are located inside the evaporator due to the evaporation of the seawater. If you leave them there, they are going to surround the tubes and be considered as a layer of insulation. You don't want that to happen. So what we do then is we try to get rid of these gases. So we have to have a unit or a system that vents these gases out. Normally, we don't consider this in our mathematical analysis, but practically speaking, you have to make sure that you vent out these gases so that they do not affect the performance of the unit in hand. And in all thermal power plants that are available, they have a way to get rid of these gases, not to affect the performance of the unit. Here we're talking about these gases. We're talking about, basically, we started with a temperature difference that happens for the vapor as it leaves the evaporator and goes to the condenser, losing some of the energy, which definitely reduces the system performance. In the condenser, normally, we expect that it would operate at a counter current arrangement, and there's a temperature difference between the feed water that leaves the condenser and the saturation temperature at which it will be heated in the evaporator in the order of 5 degrees centigrade. So basically, if you are talking about a saturation temperature in the evaporator of 75 degrees centigrade, then you expect to design your condenser to heat the seawater from whatever inlet temperature, say it's 25, to a value which is 70, so that it is less than the water temperature by about 5 degrees or so. This is some sort of a typical values that are found in reality, because you don't need to do substantial heating in the evaporator. Otherwise, you'll be consuming a lot of steam. And you will see that steam here is the heat source. You need to reduce the heat source to make your gore higher as much as you can. Before we get to the modeling, the elements that we will need in the model basically is something like what we have done earlier and what we'll keep on doing for the rest of the term. The combination is basically energy balance and mass balance. Sometimes just for the quality of the process, we add the entropy balance to the equation. But basically, it's conservation of mass and conservation of energy that we are basically applying for each system that we have. The boiling point elevation is, again, a point that we consider because it takes care of the difference between the saturation temperature of salty water versus pure vapor, so that it helps us to determine what is exactly or precisely the vapor temperature which is leaving the evaporator, for example. Khalid, you had a question? You raised your hand?
Yes, Doctor. What kind of losses do we have other than the prime? Do we have any other losses?
The losses that we have there are basically losses of heat transfer. So it's something related to the pressure difference, something related to the boiling point elevation, something related to the existence of the non-condensable gases that we need to vent out. Normally you have something that we call an ejector to vent out the non-condensable gases. You get rid of them in the system, but when you do that, you lose a part of the steam as well. A part of the vapor is being lost. And that's something that depends on the how good the system, how experienced it is the one that operates the venting system, so that he makes sure that he only gets rid of the carbon dioxide and non-condensable gases and does not leave the vapor to be lost. So these are the kind of losses that you expect in a system like this. Then we'll get into the basically mass balance and energy balance for the system, and then look at the performance parameter. At that stage, I might just pause for a while before we get into the details of the system performance, and just go quickly through the attendance. I find that your number is a little bit on the low side today. What kind of activities that you have? For Dawood Al-Hajdi, you asked the condensed gases, where they come from. They actually came from the ions that are in the seawater. As I said, the ions can have compounds like carbonates. Carbonates are having carbon dioxide part of. As the carbonates heat up, the carbon dioxide is being liberated. And this is one source of the problems that we face in desalination systems. Upon heating, definitely. So, Rashid Eliami?
Yes, Doctor.
Abdullah Al-Azwari?
Yes, Doctor.
Muhammad Al-Ghamdi?
Yes, Doctor.
Ahmed Al-Hussein?
Yes, Doctor.
Hadi Al-Utaybi?
Yes, Doctor. Yes.
Abdul Karim Al-Ramadan? You just asked, so I know you hear Abdul Karim. Badr Al-Safar?
Yes, Doctor.
Saleh Al-Safar?
Yes.
Okay, then we have Osama Al-Shahrani?
Yes, Doctor.
Fine. Khalid Al-Shamrani, you just asked, so I know you hear Khalid. Sultan Al-Suailim?
Here, Doctor.
Abbas Al-Yahya?
Yes, Doctor.
Hussein Al-Yusuf? Maybe Hussein is not here today. Dawood Al-Hajji?
Yes.
So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 13. Okay. طيب. Fine. Back again to our analysis, looking at this unit of the single effect